This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning. So today, in the morning and in the afternoon, we will cover Nyquist criterion. So we will cover first simpler version of the Nyquist, and then the more complicated version will be presented in the afternoon. So last lecture, yesterday, we talked about Cauchy principle of argument. So we also indicated how Cauchy can be used for Nyquist stability criterion. We didn't go into details, it was just a prelude, an introduction. So this lecture will go in much more detail to explain the relationship between Cauchy and Nyquist stability criterion, and we will state a simpler version of Nyquist. So simpler version would be when the open loop transfer function doesn't have any poles on the imaginary axis. That's the simpler version. Okay. All right. So let's see. First, motivate things. I did already yesterday quite a bit, and then we will consider Nyquist stability criterion special case. The special case is there are no imaginary poles in the open loop transfer function. So basically, we do not have, any poles of the open loop transfer function right on the imaginary axis. In other words, the D contour would not contain any poles of the open loop transfer function. So I will present a few examples and then conclusions. So these examples would demonstrate how you can use Nyquist. You will see actually that using Nyquist is very simple. Once you understand the main result, it's a very simple way to test stability. Okay? And then we'll wrap up with conclusions. And this afternoon, I will talk about the case when there are some imaginary poles of the open transfer function, and then we will learn how to draw Nyquist plot in that case. Right? The statement of the result will not change, but the way we plot the Nyquist frequency response, the Nyquist plot, will change. All right. So why do we do Nyquist? Well, first, it's an alternative test, an alternative way to check stability. It is based on the frequency response of the system, and we saw that for stable systems we can experimentally determine frequency response. It can also deal with systems that have time delays. So Nyquist criterion can be applied to systems with time delay. We can plot the frequency response. By the way, Raud-Hurwitz does not apply in that case, right? But this criterion does. So in other words, this is a more general stability criterion than just Raud-Hurwitz criterion. Raud-Hurwitz was applied to polynomials, right? So we are checking whether some polynomial has, all roots strictly in the left half plane, right? But here, Nyquist can be used for systems with time delay. It can also deal with systems where open loop transfer function is unstable. So, it's a very sort of useful, it's a general tool. And actually, Nyquist leads to these important concepts on phase and gain margins, but it leads to a lot of other concepts that are fundamental to frequency domain design. So loop shaping designs are basically based on concepts that come from Nyquist criterion. So we will introduce these concepts today. So in a particular, robustness of the system is captured to some extent with these concepts of phase margin and gain margin. In time domain, when we were doing root focus, we did not talk at all about robustness, how perturbations in the plant affect stability. Now, these concepts of phase margin, K margin, naturally capture certain measures of robustness. So this new tool allows you to treat new problems, new questions, robustness questions, which we have not addressed so far. Right? All right, so we now want to go through Nyquist. Now, there will be some repetitions from yesterday, so I will repeat some things, so I apologize, but I think it's useful if we go through some things over and over again, just so that you sort of get more comfortable with certain concepts and hopefully sort of understand them better. Just a bit of history, that's the person behind the name. So Harry Nyquist, he was an inventor, engineer. He had heaps of patents. So he's an electronics engineer, he was. He basically was motivated by work by Black. I refer to this work on feedback amplifiers. When I presented introduction to this subject, I talked about feedback amplifiers. Now Nyquist and Bode wanted to come up with mathematical tools, design tools to design these feedback amplifiers rigorously. That led to these frequency domain methods, and it turned out that these frequency domain methods are much more useful than just feedback amplifiers. They can be used for any system design. That motivation came from feedback amplifiers. This guy really did heaps of useful work in control theory. Some of these things are listed there. For us, we will mainly use his work on stability, which is Nyquist's stability criterion. All right. What we will first concentrate on is the case when the open loop transfer function has no poles on the imaginary axis. And then we will, in the next lecture this afternoon, we'll consider general case where we allow some poles to be on the imaginary axis. Okay? All right. So we want to just review things and put things into context. Remember when we talked about internal stability, we said that the system is internally stable if all four of the sensitivity transfer functions are stable. So note that each of these sensitivity transfer functions has in the denominator 1 plus lambda 0. We introduced yesterday lambda 0, that's C times G0. That's controller transfer function times Planck transfer function. That's lambda 0. So obviously, what is, this 1 plus lambda 0? Know that lambda 0 is a rational function. So 1 plus lambda 0 is a rational function. But when I find what are the zeros of f of s, they are exactly the poles of all the sensitivity functions. Right? Zeros of f of s are poles of all the sensitivity functions. Can anyone see that? Yeah? Everyone? Yeah? All right. So if these zeros of this f of s are strictly in the left half plane, then we have internal stability. Now, in the last lecture, we introduced this lambda 0, which is the product of C and G, Planck and control transfer functions, and we were interested in Nyquist's plot of lambda 0, right? Because we said that's what is used to state the Nyquist criterion. So this is just sort of putting things into context. We still are sort of motivating or reminding you what we are doing here. So the main ingredients in the Nyquist stability criterion are f of s, where lambda 0 is by definition G0 times C, right? So that's of interest. And what's also of interest is the contour in S-plane, the so-called D contour. So this D contour was introduced in the last lecture. We said the borders of this D contour are imaginary axis, where we go from minus infinity to infinity. So we are moving in the clockwise direction, right? And then the semicircle of infinite radius, right? So that's the D contour. So what we will assume, is that this contour, well, actually the way it's chosen, then this contour will completely encompass the right half plane of S plane, right? So, and what we don't want to have, we do not want zeros or 1 plus lambda 0 in this region. Why is that? Why don't I want zeros or 1 plus lambda 0 in the right half plane? Why it causes instability? That's the poles of all the sensitivity transfer functions. So zeros of 1 plus lambda 0 are the poles of all the sensitivity transfer functions. All right, so this is like main ingredients. We will assume in all of this that the open loop transfer function is strictly proper. So in other words, for lambda 0 here, we have more poles than zeros. Strictly more poles than zeros. I will assume that just so that we can state things more easily. All right. So now the question that we are asking here is, how do zeros and poles of f of s relate to this open loop transfer function? Well, all right. So zeros of f of s are closed loop poles, and poles of f of s are open loop poles, right? But lambda 0 of f of s, if we change s to travel in the clockwise direction on the contour, well, on the imaginary axis is just we need to replace s by j omega. Right? So it turns out that frequency response or Nyquist plot of lambda 0 is the way to connect open loop transfer properties of the open loop transfer function to stability or locations of poles and zeros of f of s. That's what Nyquist criterion states precisely. So what we will assume is that we know, this is an important assumption, we'll assume that we know the number of unstable open loop poles. So open loop poles are the poles of fs. And note what we said yesterday, poles of fs are the same as poles of lambda 0. Why? Because lambda 0 plus 1, that's f of s. When I rewrite everything as a transfer function, then poles of f of s are the same as poles of lambda 0. Right? Okay. So all of this, look, everything I said here is just sort of main ingredients. I'm just sort of saying this is the setting, and we want to now relate things to state stability. All right. So how do we now put these ingredients together? Well, we need to use Cauchy to conclude about stability of the closed loop from the frequency response and the number of open loop unstable zeros. So what I will do, I will basically assume that I know this. I know the number of open loop poles, unstable poles, and I will plot the frequency response of lambda 0. And then with knowledge of what this frequency plot does, and this number of open loop unstable poles, I will be able to determine the number of unstable zeros of f of s, which is basically the same as the number of unstable poles of the sensitivity transfer functions. So I assume I know this and the frequency response, and then I will conclude about the number of unstable zeros of f of s, which is exactly the number of unstable poles of the sensitivity transfer functions. So this is how we are going to put all these ingredients together. To justify this, or to explain this, we use Cauchy. So let's now look at the application of Cauchy principle. So we are assuming that, open loop transfer function is strictly proper. So we have that when, norm of s goes to infinity, well, f of s will tend to 1. Why? Because lambda 0 of s will go to 0. Because there are more poles than zeros, so what's in the denominator is larger. It's infinity compared to numerator. So lambda 0 tends to 0 when norm of s goes to infinity because of strict properties. So now we pick contour that encompasses the right half of the S-plane. We call it the Nyquist D contour. So here it is. So the Nyquist D contour, I already presented that in the lecture yesterday. We said we will pick the contour which looks like D, letter D, but the radius here is infinite. So this contour completely encompasses everything everything in the right half plane. So compass is right half plane. So what happens? Well, we can decompose this contour into CI, which is the imaginary axis, and CR, which is this semicircle of radius infinity. So since on CR, whenever we are traveling on the points here, norm of S is infinity, then from the previous conclusion we conclude, well, that on CR we have that this holds, because norm of S is infinity for any point on this semicircle. Yeah? So all points on this semicircle map in F plane into point 1. Right? So all points on the semicircle, remember in Cauchy principle, what we had? We had a contour in S plane, and then we have transfer function F. So here, F is 1 plus lambda 0. That's the choice of F that we use. And the contour is this contour, right, in S plane. Now this contour would map into F plane into another contour. So what I'm saying is that any point of this semicircle would map into point 1 in F plane. Right? That's what I'm saying, right? Everyone following this? Okay. So the whole CR collapses to this point 1, J0. Right? Now, the only mapping that we need to then consider, so nothing interesting is happening here, because as we change, S on this semicircle, we don't move. We cannot have any encirclements of the origin in F plane. Like that doesn't play any role in encirclements of the origin in F plane. So what is the only interesting thing is when we evaluate F on the imaginary axis, where omega changes from minus infinity to infinity. So you see, I told you already before, when we talked about frequency response, how we would be sometimes interested in looking at negative frequencies. I mean, negative frequencies don't make a sense in reality, right? We only have positive frequencies. But mathematically speaking, when I evaluate F for all points on the imaginary axis, I do have to consider negative omegas. And that's why, this motivates us to consider F for omega between minus infinity and plus infinity. Because we want to see what happens when we travel on this boundary of the contour, the contour. All right, I'll stop now with the last question. These are very important things. I don't mind spending more time to talk through this. Even if we go into the third lecture, I don't mind that. So are there any questions at this point? Okay, all right, so now we are applying Cauchy to state Nyquist criterion. I will use Cauchy principle to state the Nyquist stability criterion. So what I'm saying is, all the points on this semicircle CR in S plane. So now look, this is exactly the situation that we had in yesterday's lecture. What I'm saying is, I have some contour in S plane, and that's my D contour. And then I'm looking at the values of F, so where F is chosen. F is 1 plus lambda 0 S, right? So that's my F. So now looking at how F will change in F plane. Know that this is real part of F, and this is J times imaginary part, right? Imaginary part of F. Right? So what I'm now saying is, because of strict properness assumption, all points on this semicircle are mapping to this point 1, J0. All points map to that one point there. And then I'm saying, okay, well, what's the interesting thing then? Well, the interesting thing is to evaluate F at J omega. Why at J omega? Well, because J omega is actually points on the imaginary axis. And I want to change omega from minus infinity to plus infinity. Now, depending on the transfer function F, depending on this lambda 0, right? Here, points on the imaginary axis may map into some curve in F plane. Right? It can be some other contour in F-plane. In yesterday's lecture, we saw lots of examples for different contours in S-plane. We ended up with different contours in F-plane. And the mapping is the transfer function F. Right? So, now, we basically are saying points on this line map into some points. This is very arbitrary. This can take very different shapes depending on F. Right? And then there's one more step. What I would say, well, you know, what is my real part and imaginary part of F? Well, you know, if I look at some sort of frequency response, some contour in F-plane, what Cauchy was talking about was how many times the contour in F-plane would encircle the origin. You remember that was the thing we were counting. You know, I was rotating around, I was, you know, sitting in this origin and I was seeing horses. So that's what we are counting, but that's what Cauchy tells us. You know, how this F would behave with respect to the origin. How many times it would encircle the origin. But note, what is F? Well, F is just 1 plus lambda 0. So instead of plotting F, I would decide to plot just lambda 0 frequency response, and then instead of talking about F encircling the origin, I can talk about lambda 0 encircling minus 1 J0. That's the critical point. I shifted the coordinates by just 1, translating everything. So you see, if I decide to plot lambda 0, then Cauchy can tell me, you know, how many times, well, Cauchy would use how many times lambda 0 of j omega encircles the critical point minus 1 J0. Questions again? Yes?
Why is it better to plot lambda 0?
It's you know, often, you know, you would, it's not more difficult or easier, but lambda 0 you would often, so that has a very sort of clean meaning. It's open loop transfer function. Often you can sort of break the loop, you know, and find frequency response of this guy. So it's much easier to find frequency response of lambda 0 than, you know, 1 plus lambda 0. Actually, mathematically, right, you can find 1 plus lambda 0 easy, just add 1. But what you are really measuring is typically, you know, this lambda 0, this response. It's, you know, traditional. There are lots of other sort of reasons why we would work with lambda 0. What I will show you later, so working with lambda 0 is convenient for other reasons as well. When you look at these guys here, so note that all of these guys had 1 plus lambda 0, right? Now, what does sensitivity have? Sensitivity is 1 divided by 1 plus lambda 0. And what is this complementary sensitivity is lambda 0 divided by 1 plus lambda 0. Right. So what we will do is, you know, when we do frequency domain design, we will try to shape sensitivity, complementary sensitivity, and other transfer functions, sensitivity functions, by shaping one thing, lambda 0. So we will show that, for instance, when lambda 0 is large, then this is close to 1, because this 1 is negligible to that. So this is then close to 1, and this is close to 0, when lambda 0 is large. When lambda 0 is small, then this is close to 1, right? And this is close to 0. So what we would do then, we would be playing with lambda 0, which is one stone, and we want to kill 2 birds. So there will be lots of other reasons why lambda 0 would be useful, right? So I'm giving you just sort of different reasons. Right? Any other questions? All right. So now we are applying, so I'm stating here Cauchy principle applied to this setting. I chose the transfer function, that's 1 plus lambda 0. I chose the contour in S-plane, that's the V contour, and now I can state something useful in terms of stability of the closed loop system. So Cauchy applied to our situation is exactly the Nyquist criterion. So the Nyquist criterion, proof of Nyquist criterion, is exactly by applying Cauchy principle to this setting that I described earlier. So let's just see what this is. So what I'm saying is Cauchy principle applied to our case says that n plus p is z. So I need to now explain what each of these things are. So I will call n the number of clockwise encirclements of the critical point -1j0 by the frequency response of lambda 0. So I'm looking at this critical point, and we're looking at number of clockwise encirclements of that point by lambda 0 of j omega. That's my n. If I have counterclockwise encirclements, n can be negative. So n can be positive or negative, depending if it's clockwise or anti-clockwise. P is the number of poles of f of s in the right half plane. In other words, the poles encircled by the d contour. Right? The number of poles of f of s encircled by the d contour is the number of unstable open loop poles. And then z is the number of zeros of f of s in the right half plane. So it's the number of zeros encircled by the d contour. So remember what we were talking about yesterday. We were saying you have a transfer function. In this case, transfer function is f, 1 plus lambda 0. And then we said, let's see how contour of f behaves in f plane. And we were looking at encirclements of that contour of the origin by that contour, either in clockwise or anti-clockwise direction. So what this tells you is that when you apply Cauchy, right, to this situation, you basically have that n plus p is equal z. That's what Cauchy states for this special case. Now, if I assume that I know p, right, p is the number of unstable open loop poles. I would count n because I plot the frequency response of lambda 0, and then I count the number of encirclements. If I know my frequency response, or Nyquist plot of lambda 0, I can count the number of encirclements of -1j0, right? And then that sum, n plus p, gives me z. And z is the number of zeros of f of s in the right half plane. But zeros of f of s in the right half plane are exactly the poles of the closed loop transfer functions. So basically, z here, which stands for 0, that's actually the number of poles of the closed loop system in the right half plane. So obviously what we want z to be 0. We don't want any poles of the closed loop transfer function in the right half plane. Yeah. Questions? Again, I'm just trying to get some sense of where you are. Yeah.
The open loop I have to know it before I apply it.
Yes, that's an assumption. We always assume that you know the number of unstable poles. Yes. By the way, I mean, you may say, well, why this is, reasonable? Well, if I know my plant transfer function, typically, you can assume, right? You know whether the plant is stable or unstable, right? You would know your controller. But 1 plus control plus this would give you a totally different thing, right? Which is presumably, harder to figure out what is the closed loop poles. So look, don't just think about what is easier or harder. This method will lead to a lot of other useful tools. And from stability point of view, you might say, oh, I'm just using MATLAB. I don't care, right? But this leads to there's lots of benefits, and especially robustness and performance can be put under one single umbrella and treated in one unified way by using frequency domain methods. This is something that you can't do elegantly by you looking just at poles and structure, root locus, and all the things that we did so far. So this gives you much more powerful set of tools. Stability is useful. It's an extra tool, right? Extra result. But there are multiple benefits of these results, which you will just see. You will keep seeing the benefits of these results for the rest of this subject. Right? Any other questions? All right. Okay, so just some comments. If the frequency response, whenever I say now frequency response, I mean frequency response or Nyquist plot of lambda 0, open loop transfer function, right? So if it encircles critical point counterclockwise, then n is negative. So what this means, if we have any open loop unstable poles denoted by P, then to have stability of the closed loop, the number of encirclements of the critical point should be n is equal minus p. Why I'm saying here n is equal minus p? Because I want z equals 0. If z is, that's what I want. So when z is 0, the closed loop system is stable, right? So n should be minus p. So p should be encircling counterclockwise. The frequency response, or Nyquist plot, should be encircling the critical point p times in the counterclockwise direction to have stability. If it doesn't, you don't have stability. If it does, you do have stability. This is necessary and sufficient condition. Right? So, and that's the stability, that's the Nyquist stability criterion. So I will state this more formally, but let me just go through comments first. So we have this transfer function by Cauchy, n is equal z minus p, where n is the clockwise encirclements of origin by f of s, z is the number of unstable closed loop poles, or zeros of f of s, which sit inside the Nyquist D contour, and p is the number of unstable open loop poles of fs. Right? Open loop poles, lambda 0 poles are the same as fs poles. Yeah. All right, so this is the Nyquist stability criterion, precisely stated. So it says here, suppose that there are p unstable open loop poles, then the closed loop system is stable if and only if the Nyquist plot, so you can think of its frequency response, lambda 0 of j omega, or Nyquist plot of lambda 0, encircles the critical point minus 1 j0 p times in the counterclockwise direction as s traverses the D contour in the clockwise direction. So what I need to do, I need to plot lambda 0 when omega goes from minus infinity to infinity. So omega will be a parameter on this curve. For every fixed omega, that would give me 1 point on the lambda of j omega. And then I see how omega, as omega changes from minus infinity to plus infinity, there will be an arrow on that plot that shows me which direction I'm going. And that arrow should be such that this guy encircles this point p times in the counterclockwise direction. That's necessary and sufficient condition for stability of the closed loop. I want you to digest this. Right? So I give you the number of unstable open loop poles. I give you the frequency response or Nyquist plot of lambda 0. And then I see how many times this lambda 0 encircle the critical point. If the number of encirclements in the counterclockwise direction is the same as the number of unstable poles of the open loop transfer function, the closed loop system is stable. If this is not the case, the closed loop system is unstable. All right. So we are interested, obviously, in z equals 0, right? So n plus p should be 0. That's what we stated earlier. So closed loop is stable if and only if n is equal minus p. Minus p means p counterclockwise encirclements of the critical point by lambda of j omega. So finally, note that these encirclements of the origin in f-plane correspond to encirclements of minus 1 j0 for this guy. So we already talked about this translation. That's why, because of this 1 plus lambda 0, so instead of looking at f j omega and encirclements of the origin of that guy, we can look at encirclements of this point by this thing, because we just shifted everything by 1. Special case is when the open loop transfer function is stable. So what would be the statement then? So if this guy has all poles with strictly negative real parts, then the system is stable. You know, I should say if and only if the plot of this guy does not encircle. Right? So P is 0, hence N should be 0, so that Z is 0. So here, when P is 0, we want Z 0, so N should be 0 to have stability. And that's necessary and sufficient condition for stability. So this is a special case. So when open loop transfer function is stable, we should not have any encirclements of the critical point. That's it. Questions? All right. So here is another trick. If I sometimes give you in exams the following setting. I'm saying, all right, plot for me, you know, or check stability of 1 plus k lambda 0 when k is some gain. I give you k gain 100 or 2000, or I say for which values of k the system will be stable. You can do this by plotting lambda 0 j omega, but then you're looking at the slightly modified critical point. The critical point is then minus 1 over k j0. Now you may ask yourself, why is that? Well, I divide everything, when k is non-zero, I divide everything by k, so I have here 1 over k. So your point, critical point is 1 over k. You can also ask, we can think of this differently, you can plot k times lambda 0 and still keep the critical point the same. What is then, if you have lambda 0, what would be the, so you have lambda 0 j omega, what would k times lambda 0 look like? If I know lambda 0, I give you lambda 0, I'm asking you, plot immediately for me k times lambda 0 j omega. What would this look like? Know that if k is positive, the only thing that changes is the magnitude. So you're sort of scaling it radially from the origin. So if your lambda 0 was here, I give you k equal 2. At that phase, lambda 0 was intersecting this line here, then k2, you have to take twice the magnitude. So it just scales radially, but the phase doesn't change. Obviously, when k is negative, that's a different story, right? You would need to change the phase as well. So you get the sort of idea. So these are all tricks, but let's now look at some examples. So now we'll just go through several examples to we will now apply Nyquist criteria. So you see, it took us a lot of time to arrive at the statement. And I wanted you really to understand where Nyquist comes from. It comes from Cauchy principle. So we've done all that. Now let's just use the result. So you can see that using the result is very easy. It's very easy. So here is the example. So lambda 0 is given here. 1 plus, s plus 1 squared. So what are the poles of the open loop transfer function? Minus 1. There are 2 of them. Are there any poles of the open loop transfer function that are unstable? No. So P in this case is 0. Right? So then you plot lambda 0 j omega. This is what lambda 0 j omega is. So when you write it as real part plus imaginary part, this is what you get. Right? So what you do, you substitute instead of s j omega, and then you simplify, and you can write it as real part plus imaginary part. Yeah? So now I change omega from minus infinity to plus infinity. Right? So I get this plot here. So by the way, I found for you several points. So I'm saying there, what is lambda 0 at 0 when omega is 0? Well, lambda 0 at 0, I substituted here j omega, but omega is 0. So this is 1 divided by 1. Yeah, everyone sees that? Yeah, so that's this point on the graph. Right. So what is lambda 0 at omega equal to 1? Well, you can find from these above calculations that you get this red point corresponds to the red calculations, right? And blue point, lambda 0 at minus 1, is this point. So you can see that by the way, this plot here is generated by MATLAB. Know that MATLAB gives you an arrow on this plot. What does arrow indicate? Arrow tells you in which direction omega grows from minus infinity to plus infinity. That's what arrow means. Because this plot has a parameter in this plot, we have omega. And omega will change from minus infinity to plus infinity. So basically, for omega minus infinity, that's the point that we are from above. So as we increase omega from minus infinity to plus infinity, the plot does this. So this is the image of lambda as S takes values on the imaginary axis, j omega, from minus infinity to plus infinity. That's exactly what it is. So now, does this guy, so by the way, what is the number of clockwise encirclements of minus 1 point, minus 1j0? This point, minus 1j0, is somewhere where? So it's somewhere here. Are there any encirclements by this graph of this point? No. The point is totally outside. So that's, you remember, so my C is outside the track where horses are racing. So I'm sitting here, so there are no encirclements, right? So by the way, here, number of encirclements is 0, right? Because we read it from the graph. Number of unstable open loop poles is 0. So what is the number of unstable closed loop poles? Well, that's 0 plus 0. That's 0. So the system is stable. Very easy to use. Very easy to use. Let's look at the next example. So here is another transfer function. So what are the poles of this open loop transfer function? Lambda 0 is the open loop transfer function, right? So we have now poles minus 1, minus 2, and minus 3. All of them are strictly in the left half plane. No unstable open loop poles. So P is 0. So basically, open loop have plane poles is 0. So in this case, this is the arrow. As we go from omega minus infinity to plus infinity, we do this. We go this, and then we go from above here. This arrow indicates the direction in which omega increases. Are there any encirclements? Are there any encirclements on the critical point? By the way, this red dot here is the critical point. There are no encirclements. So no encirclements. So N is 0, P is 0. What is Z? Z is N plus P. 0. Again, the system is stable. So note this red thing here. It says here, if lambda 0 were scaled by a large positive real constant, so that's my K. I'm talking about now this situation here. So I'm saying we're scaling everything by K, and K is large. So in other words, what I need to do, my critical point would be minus 1 over K. As K is large, this critical point is approaching the origin. It's getting closer and closer to the origin. What happens then? If I scale everything with positive large K, well, this critical point will start moving this way, this way, this way, and eventually it will be encircled. It will be encircled. So let's now count encirclements. Instead, we would get 2 clockwise encirclements of minus 1, and the closed loop will be unstable. How do we count these clockwise encirclements? Note, as omega infinity is this point, but it comes, this is the bottom part, and now critical point is inside. So as I go around, I sort of go this way, and this is the first encirclement. One clockwise encirclement, and then from this point here, I encircled it again. Why have I encircled it? If I was sitting inside at this point, as omega was changing, I would have to make 2 full rotations by looking at it, right? 1 rotation, 2 rotations. That's going more in clockwise direction. Yeah? So now this tells you the system would become destabilized if I apply high gain to the open loop. You can see, you can easily, analyze high gain control. What would be this situation in root locus case? Let's go back to root locus now. Root locus exactly considers this situation, where now lambda 0 is my transfer function in the root locus. What are the poles and zeros of the transfer function in the root locus? Well, there are no zeros. there are 3 poles. All stable poles, when you think about what the asymptotes are doing, 3 asymptotes. 2 would end up in the right half plane. For high gain, from root locus, you can figure out that this will become unstable. From Nyquist, you can conclude the same. Right? It's very cool, right? So we are able to analyze one and the same problem using totally different mathematics, totally different tools. But there will be lots of benefits. This is not just saying, okay, let's double up, something, like the same tool, let's do 2 different versions of the tool. This will have multiple benefits later on, we'll see. So this is very cool. I'm quite excited that you're learning about this. Here is another one. Now what I gave you here is open loop transfer function has 1 unstable open loop pole. When you plot the Nyquist plot, this is the Nyquist plot. So here are the arrows. So what is the number of encirclements? So -1 point. This is the critical point, -1. There are no encirclements. But I have 1 unstable pole. No encirclements, 1 unstable pole in the open loop transfer function. The system won't be stable. The system won't be stable. So note, if I now scale lambda 0 by a large positive constant, this critical point will be moving inside. Imagine that the K gain is large enough, so critical point is inside. But now, this is what? Clockwise encirclement. Does that help? Does that help? No, because we will actually be even more unstable. Right? Know that Nyquist tells you exactly how many unstable closed loop poles you have. It tells you exactly how many closed loop unstable poles you have. Right? So I hope that you see that this is not hard to use at all. Obviously, you need to plot these Nyquist plots. In the exam situation, I typically give them to you. You are lucky because, when I was a student, our exams would be under 4 hours, and we had to plot everything by hand. Body plots, Nyquist plots, everything by hand. So you write formulas like this, and then you basically do point by point, you connect them, that's how you go, right? Solving your exam. So that will typically give you the frequency response. So it will be easier for you. Alright, so this is an example just to say, alright, 1 stable pole. I'm just going through more examples. 1 stable pole. What are the Nyquist plots? This is basically Nyquist plots of K over S plus 1, and I plotted them for different values of K. Note, there is 1 stable pole. Critical point is here. None of these Nyquist plots would encircle this guy. So because there's no encirclements and there is no unstable open loop poles, we get stability for all K, right? Note how larger K sort of increases the amplitude but doesn't change phase. So sort of radially, we sort of grow the amplitude by the amount of K, but the phase wouldn't change for these points, right? So we get this sort of plots for K 0.5, 1, and 2. Here's an unstable pole. In this case, the number of unstable poles is 1. And now, it will depend, on the K, whether the frequency response or Nyquist plot would encircle or not. Right? So note, for K 0.5, we have n is 0. So the closed loop system is unstable. Because we have 1 unstable pole, the plot should encircle once, the critical point in the right counterclockwise direction. So for K equal 1, Nyquist plot passes through the critical point. What would this correspond to? Well, we would say it's marginally stable. The closed loop system would have some poles on the imaginary axis. We have marginal stability. And when K is 2, we have n is -1, we have stability. Remember what is the root locus of this system. You have one pole in the right half plane, but the real line is part of the root locus. So as I increase gain, I would eventually go to the left half plane. So you can see that now what happens in the Nyquist plots, right? Here is a system, second order system with very low damping. By the way, sometimes MATLAB gives you figures like this. You can zoom in, but here you don't see whether it encircles this way or that way or passes through. So you will need to sort of do a bit of zooming in. But, you know, we did plot things for second order systems, you know, and you would know that you do not touch the real line. You stay on one side or the other side. So you do not have any encirclements, so we would have stable closed loop in this case, right? Two real poles, this is what the things would look like, you know, two stable poles. You know, by the way, whatever you plot in Nyquist, you can reproduce in Bode, right? So you can really have close relationship with this, like a close relationship with Nyquist and Bode, right? So that's just giving you here Bode picture, but here we have P0, no unstable open poles. There are no encirclements at this point, and then we have stability. What happens if I scale this by very large K? Like K times lambda G0, right? Well, this plot would start looking like this, you know, like this. But it would never, ever cross the point because it does not intersect a real negative real axis. This thing converges to zero, but it never intersects the negative real axis. So you will have stability for all, you know, a large K. However, as you increase K, this plot will get closer and closer to this point. You will see that has implications for robustness of stability. Because if your model is slightly wrong, you might actually cross around, go around. So if the model is really a little bit wrong, you may cause instability. So we will understand and analyze what is the distance or the shortest distance of this plot to this point. You will see it has connection to the sensitivity peak. This is the peak of the magnitude of the sensitivity function. It's related. Effect of delay, if I have two stable poles but I have a delay, you will see that Nyquist plot will be like a spiral. Now Nyquist plot always intersects the negative real axis. And obviously high gain will always cause problems. Because if you increase gain, this critical point moves here, so you start having lots of encirclements, and that usually causes instability. So even a small amount of time delay is very detrimental for stability. All right. So what we did, we considered special case of Nyquist criterion where open loop doesn't have any poles on the imaginary axis. It is based on Cauchy principal argument, and we will consider more general cases this afternoon. Questions? All right, I need to run. If anyone wants to ask questions, I'm sorry I can't do it today because I have to present another thing, and then I have another lecture, so it's just back-to-back things. So I'm running to another meeting. Sorry about that.
negative, and I'm pushing